All right, welcome to Chapter 2, lecture on acids and bases. Let me get set up. All right, so acids, bases. This is without a doubt the most important concept that we're going to see. If you don't get this, you'll be memorizing, and that will be very difficult. So I'm going to try to make sure my outline follows the book as much as possible. So we're in Chapter 2, acids and bases. We are going to start with just a broad overview, and then we'll dive in. So essentially, we're talking about pluses and minuses. See this sort of symbolism a lot. A plus type of charge is an acid. A negative is a base. Things aren't always charged. Okay, there's partial positive and partial negative. Just some synonyms or other terms. They're not all synonyms, but cation, anion. Some of these you've heard before. We'll introduce some other terms along the way called electrophile. Means electron loving. Nucleophile means nucleus loving. And we'll see much later in the course oxidant and reductant. That's far less important. Okay, but these are just some terms. There's a nice handout that I've given you. There's a color version that'll be available, or that is available on the either ReggieNet or somewhere. Okay, it'll be on my website or ReggieNet. We're going to be pushing a lot of arrows, and what we mean by that is arrows will explain where electrons go. All these arrows, all the explanations we're going to use for reactions can be explained by these terms. Okay, this is the most important concept, so I want you to spend a lot of time learning Chapter 2. We're going to talk about mechanisms, and mechanisms are step-by-step descriptions of reactions, and those mechanisms they become complex because of many options, many simple negatives attacking positives, okay? So each individual negative attacking positive may not be that complicated, but it's the combination of these things that becomes complicated. So just a brief historical background that the text doesn't necessarily go into a whole lot. There's the original sort of acid-base definition was the Arrhenius. So I'm going to give you three different definitions as we go here. Arrhenius won the Nobel Prize in 1903, and an Arrhenius acid was H+. An Arrhenius base was OH-. Right? They understood that hydroxide and protons would interact with each other, base and acid. Okay. And so there's no such thing as H+. Just to make that comment, I'll say that throughout the course. H+ is not a real thing, so sometimes you'll see me put quotes around it. Okay, but you've all seen this before. Water and HCl can interact. We call this process dissociation. The H goes from the Cl to the water to give you H3O+ and Cl-. Technically, there's not even any H3O+. The last literature I read is something like H2O6 for each proton. Okay, so there's 6 molecules of water to each extra proton. But the point is this is a proton down here, or it's a proton source. Okay, my pen is not behaving. So this proton source is important, okay? But the Arrhenius definition, really, of H+ and OH- is not very useful, okay? So it was short-lived, or at least Bronsted came along and further expounded on all this, okay? So this is just more history, Arrhenius, okay? 2.1 is all about Bronsted-Lowry acids. And again, you are familiar with this we want to look at these from an organic perspective. Okay, so what is a Bronsted-Lowry acid? Well, if we have a hydrogen atom, right? Think back to chapter 1. Hydrogen atoms have one electron and a proton, right? So we define this as H dot. Okay, those Lewis dot structures, we put electron around there. So if we lose an electron, and again, this isn't necessarily happening because minus one electron, it's not necessarily happening because H plus is always bound to something. So I want you to remember that. But the idea is it's one electron less than a hydrogen atom. All that's left is a proton. Okay. So that's what we mean by proton transfer. Okay. We're going to be transferring protons like crazy. So that's what a Bronsted-Lowry acid is. Bl is Bronsted-Lowry. It is an H plus donor. It's something that is donating an H plus, like H3O plus. Okay. So again, they don't exist by themselves. They're attached to something. So H3O plus is giving up an H plus to make water. Okay. So a Bronsted-Lowry base is just the opposite. It's the acceptor. And this definition is far more useful than Arrhenius. Acid has to have a hydrogen atom on it. And a Bronsted-Lowry base must have an available electron pair. There are two major ways. It can be a lone pair, like water, or it can be a multiple bond, like a double or a triple bond. We'll see example after example. So in your book, you can see a whole bunch of examples. I don't need to write these out for you. Figure 2.1 has inorganic acids or inorganic Bronsted-Lowry acids, HCl, H2SO4, etc. Okay, water can be an acid or a base, depends on what it's reacting with. Okay. Let me go ahead and write out a few examples. HCl is probably the most familiar to you, hydrochloric acid. I want you to remember something, memorize this. You don't have to memorize pKa's, but I'm going to give you about a handful to memorize. Okay, we're going to talk about what pKa means. pKa -7. HCl is the best acid you're going to see, along with a couple others. pKa -7 is essentially as acidic as it gets for our purposes. What I want you to really, really remember, because people get confused about this one, H2SO4 has the exact same pKa. We'll draw out these structures and everything. That is sulfuric acid. So it is, again, about the strongest acid you're going to see. Lower pKa, stronger acid. We'll develop this in a second. Now, an organic acid, let's draw out my CH3. It's not nearly as acidic, but it's an organic molecule. These up here are called inorganic acids. Okay. This is organic because it's got carbon-hydrogen bonds on it. The pKa here is only 5. Okay. We're going to talk about this, but HCl is 10 to the 12th times more acidic than acetic acid. This is called acetic vinegar. Okay. Just vinegar. Okay, water has a pKa of 16, 15.7. Okay, so we'll talk about pKa a lot more. But these are a few acids. Okay, I really want you to memorize HCl and H2SO4 are two of the strongest acids that you'll see. You'll see sulfuric acid a lot. Okay. All right. So let's look at a couple bases. Again, water can be an acid or a base. Acidity and basicity are relative to what is reacting. Okay, so water can be an acid or a base. The lone pairs, we're going to show arrows a lot, can reach out and grab an H plus, okay, like they did with HCl. So there's lone pairs. There's lots of examples of those. And then also, there are multiple bonds. We'll get to all this stuff in good time. But the multiple bond can pick up a proton. Okay. So acids and bases, Bronsted acids and bases specifically. Okay. One thing that's really important is charge. We'll talk about this. We talked about formal charge and all that stuff. Charge, positive, is generally acid. Okay, we're going to talk about how these trends a lot, but negative, generally a base. Okay. Not always, but generally. All right, so let's talk about the reactions of these acids and bases. It is always a transfer of a proton from an acid to a base. Okay, so let's draw out a very general scheme. Base with a pair of electrons is going to interact with this acid, HA. It's a proton bound to something. Okay, A is nothing real, it's imaginary. Everything is in principle in equilibrium. That's really important. Everything can go backwards and forwards in principle. Okay, we're going to see in practice that's not the case. But what we're going to see is a proton transfer reaction. And in fact, both directions is a proton transfer reaction. And this is where we use arrows. Again, this is section 2.2. This is just like in the book. Okay, that base is going to reach out. That pair of electrons is going to reach out and attack that H. And hydrogen, as we know from chapter 1, can only have one bond to it. So as this forms a bond here, this has to leave. It has to disconnect. So that's the left to right sense. And the opposite is true. Depending on the strength of each base and acid, then this could also happen. This is just the reverse process. Okay, so those are the arrows we're talking about. The arrows always, always, always start at a pair of electrons. Okay, there's some rules that you cannot violate in organic. Okay, you cannot have 5 bonds to carbon. You cannot arrows always start at a pair of electrons. All right, so what's going on here? The base over here, the B, is gaining. This is a gain of protons. This is a loss of protons. And the opposite is true. Over here, the BH plus would be losing the proton. The A minus would be gaining. All acid-base equilibria will follow this. You have a base and an acid. Let's just write that out. Base, acid on one side. What do you have on the other side? You have what we call conjugates. This is a conjugate acid. It is the conjugate or corresponding acid of the base. These two are connected. Base, conjugate acid. You can easily call this over here the acid and that over there the conjugate base. And the same is true here. Acid and conjugate base. They just go together. They're connected. This acid is connected to this conjugate base. So conjugate just means corresponding. The net charge is 0. So on the left side, you have no charges. On the right side, you have a plus and a minus. And another very important point is arrows start at electrons. See these electrons? I'm circling them. The arrows always start there. They don't start at the negative charge. Notice I did not start my arrow at the charge. Charges don't do anything. Okay? Lone pairs do the work of deprotonation. So let's look at a couple real examples. Let's look at 2 with water. Now we have a much stronger base, and we're going to talk about trends as to why this base is stronger later. This pair of electrons, you could pick either one, but you can't pick the charge. The pair of electrons, the arrow starts at that pair, deprotonates There's 2 lone pairs on the water, deprotonates. These electrons between the hydrogen and the oxygen break apart and go to the oxygen. So we're not worried about where the equilibrium lies at this point. I want you to understand the left and right concept, conjugate acids and things like that. Okay. So deprotonation, this is the acid right now. This is the base. On the right side, we have a base. Notice both bases are negatively charged, and we have an acid. Okay. Now, again, we could put conjugate on either side. The conjugates go together, meaning there's a conjugate, either the 2 on the left are the conjugates or the 2 on the right are the conjugates. Doesn't matter. Okay. So let's just call this one the conjugate, because right now we're not worried about left or right. Okay, these are the conjugates. It just means that this base and this acid are connected. Every single one of these, you'll have an acid on one side and a base on that side, and then the other side you'll have an acid and a base. All right. So, yeah. Truth be told, in this case, water is going to be an acid. This is a stronger base. It would go towards the right, but we're not. We'll establish that. So let's see when water is acting as a base now. Remember we said HCl is the strongest acid you'll see. Again, in principle equilibrium, in practice this is going to go to the right. Now I want you to see the arrows. Starts at a pair of electrons, attacks H. This is called dissociation. So what do you get is H3O+. Cl-. Notice we're not counting ownership of electrons and all those things. We're assuming that. You got to get that down. So chapter 1 is very foundational, and then chapter 2, extremely important. So base, acid, conjugate, acid, conjugate, base. Okay. Lone pairs attacks, not charges. Okay, lots more examples. I'm going to give you some sort of take-home examples here. Think about, I want you to fill in lone pairs. I want you to think about what happens when on HCl. If there are not lone pairs, they're implied. Okay, I gave you this one because it's a carbanion. It has to be there, but I want you to see it. Okay, it's a very important lone pair. The other ones are all important. I want you to fill in the rest of them. There's lots of lone pairs that I have not included here. Okay, so what happens when all of these things interact? These are 4 reactions. I want you to take them home and sort of thought them. It's a CH3 there. Okay, so the O- is a key thing here. That's CH3 there. So we have 4 reactions. Think about those. Again, another term that we'll use later is electron-rich species reacting with electron-poor species, nucleophiles and electrophiles. Okay, but right now we're focused on Bronsted acid and Bronsted base. Okay, so that's an introduction to reactions. Now let's look at 2.3 is acid strength and pKa. Okay. Acid strength and pKa. Better proton donor, stronger acid. Pretty simple concept. The better something is at donating a proton, the better it is, the better acid it is. Okay. It's essentially KEQ. Again, you're familiar with this. It's the equilibrium constant. Okay. So let's look at sort of the classic dissociation of an acid in water. Okay. So imagine HCl, and you get, what do you get? You get A minus, like Cl minus, and you get H3O plus. There are strong acids and weak acids. For our purposes, we're not that worried about this. So acetic acid, for example, is a weak acid. It doesn't fully dissociate in water. That's what that means. Okay. HCl does, for example. So it depends on what A is. Okay. And really what we're going to find is the nature of A is key here. We're really going to be looking at bases, but we're talking about pKa, and that is, let's look at what the KEQ would be. Equilibrium constant of this reaction would be what? Concentration of products over the concentration of starting materials. How much product is there and how much starting material? Okay, it's an equilibrium constant. So what is that? Concentration of H3O plus, concentration of A minus. Those are the products over HA and concentration of water. Okay. You will not have to do any calculations on the exam. I will give you, there might be some calculation problems on LearnSmart, and you might want to do some in the back of the book and through the book and all that stuff to practice to understand concepts. But I'm not going to ask you to bring a calculator to an organic exam. Okay. What we do is sort of some tricks. H2O is constant, basically. We can drop it off, and so what happens is we have an Ka. It's an acidity constant. And all it means is it's a KEQ for an acid-base reaction. Because you can have a KEQ for any kind of reaction. When you have a KEQ for an acid reaction, then you get H3O plus, A minus over HA, right? And then you take minus the log of this, minus the log of the Ka gives you pKa. Okay. All that does for us is, let me give you ranges. For Ka, you have a range of 10 to the minus 50th, all the way up to 10 to the 50th. This would be the strongest acid. Okay. And when we take minus the log, we sort of invert things and flip it around. Okay, so the higher number here means there's more products, means better acid. Okay, so essentially what happens is when you take minus the log, right, you're converting. All we're doing is converting this to more usable numbers, and what we get is 50 to about negative 10. This is the strongest acid. Okay, because the higher, the more products you have, 10 to the 50th, right? Then it correlates to the lower pKa number. All right, so those correlate, but there's no direct correlation. So we flip it around, negative 10 or negative 7, right? I mentioned that HCl is negative 7. Negative 10 all the way up to 50. These are the weakest acids you'll see. Okay? These are the strongest acids. We've just done this so we have whole numbers so we can have a language that we can use. It's a very useful convention. Okay, I don't want you to overthink this. I want you to think it through and understand it, but I don't want you to overthink it. 50 are things like methane. True alkanes, which we'll get to in the next chapter, are never, ever going to give up their protons, or almost never. All right, very, very weak acids. Things like HCl, H2SO4 are very, very strong acids. Then there's everything in between. Water is 15.7. Acetic acid is 5. Okay, and there's a whole range. Okay, so it's a logarithmic or exponential scale that makes it very much easier to work with us. Smaller pKa, stronger acid. I want you to get good at using the table. Again, work the problems to use the pKa table that is on page 67, table 2.1. There's some selected ones. The appendix in the back of the book, I believe it's appendix 2, is also a fuller version of this. Okay, so get very good at using the pKa table. Now, what I will say is you won't be given, it's appendix A. Okay, appendix A is your pKa's. You will not be given the pKa table on any exam. So I'm going to teach you trends beginning in section 2.4. Okay, so that's kind of just the background of the math. Okay, we're not going to do a lot of math, but smaller pKa equals stronger acid. There is an inverse relationship. Okay, now this concept is very, very important. I'm going to write this down. Inverse relationship between acidity and basicity. What do we mean by that? This is where the conjugate thing comes in. Strong acid, by definition, when you take off a proton, it is a weak conjugate base. Strong base, by definition, when it picks up a proton, it is a weak conjugate acid. So some examples. HCl we've mentioned. Please remember this one. Just memorize it. pKa -7. So that means Cl- is the conjugate base, and it is very weak. Okay, so I want you to memorize something. HCl, pKa -7, very, very strong acid. By definition, Cl- is a very, very weak base. We're going to talk about why, but I want you to memorize that halogens, F-, Cl-, Br-, and I-, that last column before the noble gases, are weak bases. So Br-, I-, F-, they're all weak bases. Okay. For our purposes, I will make it a point, if we break this rule, we will never use these to deprotonate, at least not an organic one. Okay, we might make some assumptions at some point. We will never, these will never pick up a proton. So I'm emphasizing for a reason. Okay. All right, so that's one example. Let's look at the opposite end of the sort of extreme here. Let's look at a very weak acid, methane. Look at these in chapter 3, pKa of 50. Very, very weak acid. There's actually tricks you can play on methane and other alkanes to make this happen. Not that easy to simply deprotonate it, but you can make what's called methyllithium. Very strong base. Conjugate base, but weak, strong. So the weaker the acid, the stronger the base. The stronger the base, the weaker the acid. The stronger the acid, the weaker the base. Okay? So memorize this one too. Don't deprotonate this. So you got other things in between. Again, I said acetic acid, pKa of 5, water, pKa of 15.6. You can draw out a bunch of acids and draw out their conjugate bases. Go through table 2.1. All right, so let's do some more practice. I want you to get used to looking at table 2.1, so I'm going to give you some take-home. Which is the strongest acid? I'm going to let you decide. This is called propane. Again, we'll get into a lot of these naming things. So look these up. Which one's the strongest and how much? Appendix A. Go to Appendix A. And look up these molecules. Okay. Then what you should do is draw the conjugates of all of these. What happens when you deprotonate each one of these? I'll circle that one of these H's is the acidic one, okay? But otherwise, H, one of those H's, that H, that H, that H, okay? And then draw the conjugates. I'll give you some more to draw the conjugates. I'm going to give you a potential acid. You draw the conjugate base. For this one, also draw a conjugate acid. Okay, so draw a conjugate base over here and also draw a conjugate acid. You could do this with all of them, okay? And there's a table for you to see the answers and such, okay? So work through a lot of those and do that as soon as possible so that when we talk about the trends, it's going to make more and more sense, okay? Okay. We'll break this in half, and this will be the first part. This will be an intro, and then we're going to talk about 2.4 is predicting the outcome of acid-base reactions. And then that's just a lead into 2.5, the factors that determine acid-base strength.